lot more than 10 left.
Expecting the corn to be shell now.
Yeah.
In the early 1900s, electricity was a new idea. Henry Ford was producing the first automobiles, and the telephone had just been invented. At that time, many aspects of modern technology would have seemed like science fiction, but scientists were making a lot of discoveries in a short amount of time in one particular field, the structure of the atom. I learned about all this in chemistry, where I was fascinated by the subject. I ended up having one of the highest averages in the class in chemistry, and to tell you all more about this, I've done some more additional research. I know that most of you have probably learned some of this in your own classes, but I want you to understand how rapidly these discoveries were made and their impact on modern science, which we all rely on today. With this speech, I'll give you information about the discoveries made regarding the structure of the atom in the early 1900s, specifically from 1897 to 1926. I will tell you about J.J. Thomson's discovery of the electron, Ernest Rutherford's gold foil experiment, Niels Bohr's model of the atom, and Erwin Schrödinger's model of the electron cloud and wave equation. To begin, I will tell you about J.J. Thomson and his discovery of the electron. In 1897, J.J. Thomson discovered the electron with a cathode ray. In the cathode ray experiment, Thomson had high voltage through a tube. The particles that emitted from that high voltage would flow from a negative electrode called the cathode to a positive electrode called the anode. According to sources at khanacademy.org, Thomson set up oppositely charged plates near the cathode ray. The particles in the ray went toward the positive plate, so the particles in the cathode ray had to have been negative. To understand this, think about a magnet, how the negative pole is attracted to the positive pole. These negative particles in the ray were later called electrons. This led Thomson to think that the model of the atom looked like plum pudding, with the negatively charged electrons in a soup of positively charged particles. Although his discovery was groundbreaking, his model was soon corrected by New Zealand physicist Ernest Rutherford. According to Craig Fordenrich, PhD of HowStuffWorks.com, Rutherford shot a beam of alpha particles, which according to the online Encyclopedia Britannica are simply positive particles, toward a sheet of gold foil. Most of the particles passed through the gold foil to a screen behind it, but some of the particles were deflected and scattered. This meant that the atom was made mostly of empty space, but something had to have caused the particles to deflect and scatter. Rutherford theorized that this was a dense nucleus. Therefore, the particles were not simply mixed together like in Thomson's model. Despite how influential Rutherford's theory was, he was quickly updated by Niels Bohr, and the Bohr model is still used in many science classes today. According to Matt Williams of UniverseToday.com, Bohr's model resembled the solar system. In his model, the atom had equal numbers of protons and electrons, and orbital levels around the positively charged nucleus. It would have looked something like this. Imagine my fist as the nucleus, and each orbital level around in increasing height from that. I can't make more than 2 circles because my arms are too short, but I'm sure you all get the idea. Certain electrons were supposed to occupy certain levels, but they can move levels by gaining or losing a certain amount of energy, but they do not simply fall to the nucleus and cause the atom to be unstable like was implied in Rutherford's model. Bohr's model was the model that is often used to explain quantum mechanics or the study of the movement of subatomic particles, in this case, electrons. Despite how interesting Bohr's model was and how relevant it is, his predictions didn't always work with larger atoms. Even though many of us probably learned anything we know about this from Bohr's model, Erwin Schrödinger came up with a better way to explain the motion of electrons. In another article by Matt Williams, also of universetoday.com, the electrons occupy various positions around the nucleus. In Erwin Schrödinger's electron cloud model, it would look something like this. Again, my fist is the nucleus, and it would be shaded in certain areas around the nucleus. It would be darker closer to the nucleus, and as you edged farther to the outside, the shaded area would become lighter. The darker area closer to the nucleus was said to be the most dense, and that's where the highest probability of finding an electron is. Schrödinger also published a series of equations to predict the location of these particles of electrons, and he also published the wave equation, which describes the dual wave particle nature of electrons. There is much more that I could tell you about this, but I will now draw my speech to its conclusion. I have told you about the incredible discoveries made in the early 1900s about the structure of the atom. I want you to remember that J.J. Thomson discovered the electron and published the plum pudding model, that Rutherford corrected his model with the gold foil experiment, that Niels Bohr updated the model that is often used to explain quantum mechanics today, and that Erwin Schrödinger published the best explanation and model with his electron cloud model and wave equation. I want you to understand how incredible these strides were in chemistry and physics. All of this happened at a time when most of the technology we have today would have seemed like something we would see on Star Trek now. Thank you all for your time and attention, and I hope you have learned something from my speech.